Hello everyone and welcome to this cheat sheet on triangles. In this video, I am going to cover all the properties of triangles that you will require to crack the CAT. So let's get going. Coming to the basic properties of triangles, you know that every triangle has three vertices, three sides and three angles. So to start with, sum of any two sides of a triangle is always going to be greater than the third side. If it is not the case, you will not be able to draw the triangle. Side opposite the largest angle is always going to be the longest side, and the side opposite the smallest angle is always going to be the shortest side. If two angles are equal, then the sides opposite to them will also be equal. If two sides are equal, then the angles opposite to them will also be equal. In terms of the sum of angles of any triangle, it is going to be 180 degrees. And for any triangle, the exterior angle that is formed. How do you form an exterior angle? You simply extend one side of the triangle outward, and then whatever is the angle that is formed on the outside, that is the exterior angle. We can also see that the measure of the exterior angle is going to be equal to the sum of the two interior angles that are not adjacent to it. So these are the basic properties of any triangle that you will have. In terms of classification, we can classify triangles on the basis of sides, wherein we are calling them either equilateral triangles, isosceles triangles, or scalene triangles. Any triangle that has exactly three sides or all three sides equal to each other will be classified as an equilateral triangle. Any triangle that has two sides equal to each other will be called an isosceles triangle, and any triangle that has no two sides equal to each other will be called a scalene triangle. Mind you that all equilateral triangles can be classified as isosceles, but all isosceles triangles need not be equilateral in nature. In terms of angles, we can classify triangles as acute angled triangles, wherein the largest angle of any triangle will be less than 90 degrees. If the largest angle of any triangle is 90 degrees, then we call it a right angled triangle. And if the largest angle of any triangle is greater than 90 degrees, we call it an obtuse angled triangle. In terms of triangles that have certain angles as their largest angles, we can see that there are these three things that appear. We know one obvious bit: if a square plus b square equals c square, where c is the longest side of the triangle, then we can say that the triangle is a right angled triangle because of the Pythagoras theorem. Whereas if a square plus b square is going to be greater than c square, we will see that happening in case of acute angled triangles, and a square plus b square less than c square will be seen when we have obtuse angled triangles. Also, Pythagoras theorem and its converse are going to be true always. So in any triangle that is a right angled triangle, you will have a square plus b square equals c square, and in any triangle wherein you have a square plus b square equals c square, it will be a right angled triangle. Now at this point in time, it would be beneficial for you to remember all the popular Pythagorean triplets, including 3, 4, 5, 5, 12, 13, 8, 15, 17 and 7, 24, 25. So whenever you see these kind of numbers, it will be great if you can link it back to Pythagorean triplets and are able to solve these kind of questions. Also, you have to remember 30, 60, 90 triangles and 45, 45, 90 triangles. The rule of a 30, 60, 90 triangle is that if the angles of a triangle are 30 degrees, 60 degrees and 90 degrees, side opposite to 30 degrees will be half the length of the hypotenuse, and side opposite to 60 degrees will be root 3 by 2 times that of the hypotenuse. You can also see that side opposite 60 degrees will be root 3 times the side opposite 30 degrees, and the side opposite 30 degrees is obviously 1 by root 3 times the side opposite 60 degrees. Also, in a 45, 45, 90 triangle, you will observe that the lengths of the sides are going to be in the ratio of 1:1 is to root 2, or the hypotenuse is root 2 times the two equal sides. Also, the equal sides will be 1 by root 2 times that of the hypotenuse. So fairly straightforward concept till now. Now coming to the concepts of similarity and congruence, unlike school days, you will not really have to prove if two triangles are similar, if two triangles are congruent to each other, and so on and so forth. But the identities that we are going to get because of similarity and congruence are going to help us solve questions that involve lengths, angles, and even areas. So to have a look at the triangles or a couple of triangles that are present and they have their angles equal and sides are in the same ratio, they need not be exactly equal, but they should be in the same ratio in terms of their vertices, then we call these two triangles similar triangles. Similarly, if all the angles and the sides of two triangles are exactly the same, then we call them congruent triangles. you have to remember that there has to be parity of vertices that will be present. So in case there is a triangle ABC and triangle PQR that you have here, you have to ensure that ABC will be similar to PQR only if angle A is equal to angle P, angle B is equal to angle Q, and angle C is equal to angle R. If it is any other way around, you will have to adjust the vertices accordingly. Because if you mess that thing up, then you will mess up the ratios of the sides as well. And they have to be in the ratio as that of the angles. So remember this part when it comes to similarity and congruence. There is one special case when it comes to similarity of triangles. You will see a triangle ABC, which is a right angled triangle, right angled at B. Also, we have dropped a perpendicular AD to the hypotenuse, that is AC. Now you will see that there are three triangles that are getting formed. One is the larger triangle ABC, you will see another triangle ADB, and you will see another triangle BDC. You will be amazed to know that these three triangles are all similar to each other and in this order. So triangle ABC will be similar to triangle BDC, and that will be similar to triangle ADB. So you have to understand here that the angle A that we had for the larger triangle, so this angle BAC that we have for the larger triangle will measure the same as this angle that we have here, which is DBC or CBD, whichever we want to look at it. Similarly, angle ABD will be the same as angle ACB. So these things you will have to keep in mind in this context. Now this does not end here, and there are three nice identities that we get because of this similarity. You can write down the ratios and you can try to find it out for yourself, but I'll show it to you in shortcuts. First thing, AB square is equal to AD into AC. So this line, this segment AB square is going to be AD multiplied by the longer form or the entire hypotenuse AC. So AD times AC will be AB square. Now you can guess very quickly what is going to be BC square from this particular context. And you would be right in most cases. BC square is going to be CD times AC. So now because we are at BC square, CD will be this part and AC will be the entire hypotenuse. And there is one small concept that exists here, which is BD square is going to be AD multiplied by CD. Remember these three forms, they are very important, and whenever it comes to any right angle triangle that has a perpendicular on the hypotenuse, you might be required to know these three concepts at the top of your mind. Now going to the parts of a triangle. There are many parts of a triangle. Of course, the sides, vertices, angles are all there, but we are also looking at constructions within a triangle, which include altitudes. So if you drop a perpendicular from any vertex to the opposite side, it will count as a perpendicular or an altitude to that triangle. All the three altitudes of a triangle will meet at a point which is the orthocenter of the triangle. Similarly, if you join the midpoint of a side to its opposite vertex, then that will count as a median of a triangle. All three medians will intersect inside a triangle on this point called the centroid of the triangle. Perpendicular bisectors of all three sides of a triangle will meet at a point which is called the circumcenter. And the funny thing about the circumcenter is that all the three vertices will be equidistant from this circumcenter that you will have. And this circumcenter to the vertex distance that we have is going to be the circumradius. And if you draw a circle with this radius, you will see that all the three vertices of the triangle will lie on this circle. And this circle will circumscribe the entire triangle that you have. Similarly, if you draw the three angle bisectors of the three angles of any triangle, you will see that these three angle bisectors will meet at a point inside the triangle. This point is called the incenter of a triangle, and this is equidistant from all the three sides of the triangle. So if you know the properties of perpendicular bisectors earlier and angle bisectors now, you will see that the angle bisector will be the locus of all the points that are equidistant from the two arms that make the angle. And so in this context, the point of intersection of the three angle bisectors is going to be equal to or equidistant from all the three sides of the triangle. Now, if you take this as the radius and draw a nice circle, you will get a circle that will have the three sides of the triangle as tangents to it. And this circle is called the incircle, the radius is called the inradius, and of course, the point of intersection, as we earlier mentioned, is called the incenter. So these are the important parts of a triangle that exist. One thing to remember, in an equilateral triangle, all the 4 points that I mentioned here will converge and they will basically be the same point that will be there. So this orthocenter is the same as the centroid, is the same as the circumcenter, is the same as the incenter in any equilateral triangle. In a right angled triangle, you will have one small thing that is there, which is basically the circumradius, and that will be half the length of the hypotenuse that will be there. In terms of the medians, you will see that I have constructed the three medians for this triangle ABC, and the medians are AD, BE and CF. The centroid, which is the meeting point of the three medians, will divide each individual median in the ratio of 1:2, meaning that if you have this line AD or this median AD and G is the centroid, AG is to GD will be 2:1 or GD is to AG will be 1:2. So it will divide the median into two parts such that the larger part will be 2 units, let's say, the smaller part will then be 1 unit. So it will divide each individual median in the ratio of 2:1 or 1:2. Also, every median divides a triangle into two triangles of equal areas. So if you look at the median AD here, the two triangles so formed ADB and ADC will both have equal areas. And of course, that area will be equal to half the area of the larger triangle. Also, very interesting and very important point here, the three medians divide the entire triangle into 6 smaller triangles. So if you look at these smaller triangles that we have formed, AGF, BGF, BGD, CGD, CGE and AGE. These 6 triangles will all have equal areas, and of course that area will be 1/6 of the area of the bigger triangle. In terms of the important points that are there, in terms of the constructions we had done for an acute angle triangle, all the points will be inside the triangle. So the orthocenter, the centroid, the circumcenter, the incenter, all of them will basically be inside the triangle. For an obtuse angled triangle, the orthocenter, point of intersection of all the altitudes that are there, and the circumcenter will be outside of the triangle. For a right angled triangle, the orthocenter will be the vertex of the right angle that will be there. And the circumcenter, as we saw earlier, will be the midpoint of the hypotenuse, and so the circumradius will be half the length of the hypotenuse. In terms of area, there are 5 formulas that you need to know. The first formula being half into base into height. So I'm sure all of you know this basic formula pertinent to the area of any triangle, wherein the area will be given by half into base into height. The second formula is also a well-known formula called the Heron's formula, which is root of S into S minus A into S minus B into S minus C, where S is the semi-perimeter, or A plus B plus C, sum of lengths of the 3 sides of a triangle divided by 2. The third way in which we can figure out the area of any triangle is half into AB into sine of the angle between them. So half AB sine C will be one of the ways in which you can find the area of a triangle. You can also use half AC sine B or half BC sine A to find the area of a triangle. ABC by 4R is one of the rarer formulas that we will use when we find the area of a triangle, where ABC are the lengths of the individual sides and capital R is the circumradius of this particular triangle. Area of a triangle, or for that matter any polygon, is given by small r into small s, where small r is the in radius of this particular circle that we are going to draw, which is the in circle, and s is again the semi-perimeter, which is A plus B plus C divided by 2. In terms of perimeter and semi-perimeter specifically, there is this one small identity that exists that will help you figure out the number of triangles that you can form that have a similar perimeter. So we have the longest side. The longest side will always be less than the semi-perimeter of a triangle. And why is that the case? Because if the longest side is greater than half of the perimeter, then what is going to happen? The other 2 sides will not be longer cumulatively compared to the longest side. And then you will not be able to form a triangle, because remember the very first thing that we saw in this PPT, sum of any 2 triangles or sum of any 2 sides of a triangle is always greater than the third side. Also, the longest side can be at least equal to 1/3 of the perimeter, because if it is less than that, one of the other 2 sides will automatically become longer, and that's why the side that we had started with will no longer be the longest side. Also, if P is even for any given perimeter, we will have P square by 48. So the brackets here indicate the integer that is the closest to P square by 48, and if P is odd, P plus 3 the whole square by 48, so that is the bracket that we are talking about, will be the possible triangles with perimeter P that will exist. However, it is a good idea for you to manually count the triangles for a given perimeter, purely because there will be some conditions that will be given to you in terms of the triangles being either obtuse angled or right angled, or not having any 2 sides as equal. So for that, you have to understand how to find the number of triangles of a particular perimeter using basic counting techniques. In terms of special cases, when it comes to area, triangles on the same base will have areas in the ratio of their heights, because they will have the same base, and half into base into height is the area of any individual triangle. Also, triangles having the same vertex and base on the same line will have areas in the ratio of their bases. In other words, if there are two parallel lines between which the triangles are located, the heights of the two triangles will be equal, and that's why the areas will be the same as the ratio of their bases. Also, area of any equilateral triangle is given by root 3 by 4 into side square, and one step ahead, if you explore this, any regular hexagon will be a collection of 6 equilateral triangles, and that's why the area of a regular hexagon, which we will study again in terms of polygons, will be 3 root 3 by 2 into side square. There are additional theorems that exist in terms of triangles which you should be knowing. The first one is the basic proportionality theorem, which states that if there is a triangle ABC and we have DE parallel to BC, then the sides where D and E cut the triangle will be divided in the same ratio, which means AD upon DB will be AE upon EC. Similarly, there is one small corollary that exists to this formula. If, let's say, D and E are the midpoints of AB and EC, or in other words, line joining the midpoints of any two sides of a triangle will be parallel to the third side and will be half the length of the third side. The converse for these two things is also true, wherein I am saying that if you have any triangle, if you have in any triangle AD by DB equals AE by EC, then DE will automatically be parallel to BC. Similarly, in any triangle, if you have DE as half of BC and you will have DE parallel to BC, then we can be rest assured that D and E are the midpoints of AB and AC. So these theorems will all be true. Also, one very important thing which you can remember, if let's say DEF are the midpoints of the three sides of a triangle, triangle DEF will have area equal to 1/4 of the area of the original triangle. Also, in terms of the midpoint theorem, if D and E are the midpoints of sides AB and AC, triangle ADE will also be 1/4 of the area of the larger triangle. So just remember these facts. In terms of Apollonius theorem, it's a very rarely used theorem, but in case there is a triangle ABC where AD is the median to side BC of this triangle, then we will have this very specific identity, which will be AB square plus AC square will be twice AD square plus twice BD square. Remember that it is not 2AD the whole square, but 2 multiplied by AD square. So just remember this bit and you should be fine. You can also write this as AB square plus AD square equals 2AD square plus 2CD square, because BD is equal to CD. Also, you can write this as AB square plus AC square is 2AD square plus BC square by 2, because BD is going to be half of BC. So any of these three forms is alright. You can remember this one and you can derive the other two from the basic form that we have. In terms of the angle bisector theorem, which is also the last concept in terms of triangles, there are two types of angle bisectors that you can see. One is the internal angle bisector and the other is the external angle bisector. Now in this triangle, let's say AD is the angle bisector to angle BAC. Then what is going to happen? You are going to have AB upon AC, the two sides that make the angle, the ratio will be equal to BD upon CD, the point which cuts the third side into two parts. So AB by AC will be BD by CD. What if we are talking about an external angle bisector? So let's say we have a triangle ABC, which is an obtuse angled triangle, let's say, and we extend CA to this point E, and we draw AD, which is an angle bisector of BAE. If AD is the angle bisector of BAE, then what are we going to get? AB by AC equals BD by CD. You will observe that this is exactly the same form that we had used on the previous slide. So that is one way in which you can remember this. So if you have an exterior angle BAE, this is BAE, and AD is the angle bisector, then AB divided by AC will be the same ratio as BD divided by CD. So we are basically looking at a distance from this point D wherein the angle bisector intersects the opposite side, and that will be true in all the cases, in both the cases rather, internal angle or external angle. If you like this video, do consider giving it a thumbs up and let us know in the comment section what is it that you liked about this particular video. If you find this channel to be useful, do consider sharing it with all your friends so that we are able to reach out to the maximum number of people that is possible. Also, if you have any comments or suggestions for any upcoming videos, do let us know. As I've written here, life without geometry would be pointless. We will be continuing with geometry for the next section as well. So stay tuned for the next video.